Hello everyone, welcome back to this course of material characterization. In the last class, we have just looked at the optical system of polarized light microscopy, and then we have identified and appreciated the merits of polarized light and its superiority over the bright field illumination. In today's class, we will look at the another variant of the optical microscope called differential interference contrast microscopy. Let us see what is this microscopy. Look at this slide. As usual, I have picked up some of the classical images from this website microscopyu.com. You see that the first image shows that surface defects in a high temperature superconducting ceramic single crystal. You can see that the kind of clarity and the contrast you get in the ceramic surface through DIC. And the image B is of magnetic thin films, and image C is buzz-line details in an IC board. So these are some of the best micrographs one can achieve through this DIC. We will see that what is the principle of this technique, and I have written here it is an optical system for viewing gradients in the optical path lengths. You see, in one of the previous class we just saw a phase contrast microscopy, which is an optical system that converts the optical path difference in a specimen to the contrast in the object of the image. Here DIC is an optical system that is used to view the gradient in the optical path length or optical path difference. The images produced by these systems are very distinct and relief-like and shadow cast appearance, a property of the image which makes it to appear like a three-dimensional and real. So that is why it is having some superior quality over the rest of the variants of the optical microscopes. So now let us get into the details of this DIC microscopic system. The DIC microscope employs a mode of dual beam interference optics that transforms local gradients in the optical path length into an object into regions of contrast in the object image. Differential interference contrast microscopy is a beam shearing interference system in which the reference beam is sheared by a minuscule amount, generally somewhat less than the diameter of an array disc. So please remember, in contrast to the phase contrast microscopy, this is an optical system viewing the gradients in the optical path length in an object into regions of contrast in the object image. That is, it is converting the gradients in the optical path length into a contrast of the image. We will see how it is being carried out. Let us look at the other remarks on the principles of this technique. The technique produces a monochromatic shadow cast image that effectively displays the gradient of optical paths for both high and low spatial frequencies present in the specimen. Those regions of specimen where the optical path differences increase along a reference direction appear brighter or darker, while regions where the path differences decrease appear in reverse contrast. As the gradient of the optical path difference grows steeper, image contrast is dramatically increased. The phase contrast microscope is designed to take advantage of a phase differences between the various components in the specimen and the surrounding medium. It is not simply a phase difference that is necessary, but also diffraction by the specimen must occur for the phase contrast microscope to produce a suitable image. By comparison, differential interference contrast relies on phase gradients to generate contrast in otherwise transparent specimens, resulting in the classical pseudo three-dimensional images for which the technique is widely known. But it is not that it is only popular for a transparent specimen, it has been widely used for the opaque specimens also. We will see the practical examples. I will take you to the lab, and then as usual I show the demonstration on the opaque samples, how you can appreciate how this DIC is improving the contrast. So let us look at the optical system. In DIC microscopy, the specimen is sampled by pairs of closely spaced rays, that is coherent wave bundles, that are generated by a beam splitter. If the members of a ray pair traverse a phase object in a region where there is a gradient in the refractive index or thickness or both, there will be an optical path difference between the two rays upon emergence from the object, and that optical path difference is translated into a change in amplitude in the image. So this is very important. You have to look at these two lines again and again. It is worth doing that. The image contrast basically produced from the gradient of the refractive index or thickness or both. So we will not be able to distinguish from where the contrast is coming from, whether it is a thickness or the optical path difference. We will see why we are saying so in the coming slides. In DIC microscope, two optically distinct planar wavefronts traversing a phase object become deformed and vary in their optical path length in the region of the object. Differential interference between the two wavefronts produces high contrast patterns of the phase gradient, example, between the edge of the object and the surrounding medium. So you see, we have also seen that a beam splitter in a polarized light microscope. Similar splitter is being used here also. In fact, the polarizer setup is also an integral part of this DIC system. We will see how it is. In phase contrast, the amplitude corresponds directly to the optical path difference between a specimen ray and a general reference ray. In DIC microscopy, amplitudes correspond to the derivative of the optical path difference profile and not to the optical path difference directly. That is why the name differential interference, because it is the derivative of the optical path difference profile. This is what is shown in the schematic. Please pay attention to this schematic. This is optical path difference in nanometers. This is the distance, and you see that the profile like this, that is a plot of optical path length across a diameter of a phase dense object. Why the curve appears like this? Because any light traverses through a phase object, it will deflect, or it will do something to do that light wave. That is what we have seen in the previous lectures, that is some phase shift will happen. So, look at the schematic B, the derivative of optical path length curve shown in A added to the constant gives the amplitude profile perceived using DIC optics. So, you can see that it is a derivative differential of optical path difference over a distance of small distance dx versus a distance. This is you have a perceived positive intensity and this is a perceived negative intensity. So, you see that positive and negative slopes in A corresponds to region of higher and lower amplitude. So, this is a key schematic which explains the name of differential interference contrast. We will now look at the DIC optical system. It is similar to what we are already seen. Then what is new here? We will see. Two polarizers, that is polarizer and analyzer, which we are familiar with already, and two modified Wollaston prisms, that is DIC or Nomarsky prisms are required. You have a new prism here called modified Wollaston prism or DIC or Nomarsky prism. You have the condenser DIC prism act as a beam splitter, producing two closely spaced parallel beams that traverse the object and are recombined by the objective DIC prism. So, you have condenser DIC prism that is shown here, and you have objective DIC prism here. This is what we have seen. As usual, the dots and the dash indicates the mutually perpendicular vibrations of the two components of the split ray. These two rays are nothing but what we have seen in a polarized light. It is an ordinary ray and extraordinary ray, which will have this electric vector vibrating in a mutually perpendicular direction to each other. That is the same thing here. You do not have to really get confused. Now, let us see what is this DIC prism does. The DIC prism, known technically as a Wollaston prism, is a beam splitter made of two wedge-shaped slabs of quartz. Since quartz is a birefringent, incident rays of linearly polarized light are split or sheared into two separate ordinary and extraordinary ray components. So, this is a schematic which clearly shows what is the conventional Wollaston prism. You see that the two wedge shaped slabs of quartz crystal, you can see the vibration direction is marked here. This is in this direction, another is a perpendicular direction marked, which is going through the computer screen. Okay, that is. And what you see here is the center is interference plane. And what is modified Wollaston prism or Nomarsky prism? You have the two wedge shaped slabs are there, but it is the orientation is little oblique. And what is the consequence of that? Because the orientation is oblique, your interference plane is shifted out of this prism. So, that is what it is. So, your Nomarsky prism is nothing but modified Wollaston prism. The Wollaston and modified Wollaston or Nomarsky prisms are used in DIC microscopy to generate and recombine pairs of ordinary and extraordinary rays. The oblique orientation of the optic axis of one of the wedges in the modified prism displaces the interference plane to a site outside the prism. So, this is what I have shown here. So, now let us look at how the image is formed in the DIC microscope. An incident beam of linearly polarized light is split by a condenser DIC prism into ordinary and extraordinary ray components that are focused by the condenser lens onto the specimen. The two rays follow a separate parallel trajectories like this between the condenser and objective lens A and B, these two schematic. In the absence of an optical path difference, the ordinary and extraordinary rays are combined by the object prism, giving linearly polarized light that vibrates in the same plane as the polarizer, and it is completely blocked by the analyzer. So, look at this schematic. This is these are the two rays which is coming from the beam splitter or Nomarsky prism. Sorry, it is up from the beam splitter. Then you have this object, phase object, and let us assume that there is no optical path difference in the felt by these two rays. Then the ray goes like this and they are blocked by the analyzer, because the polarized light that vibrates in the same plane as the polarizer, and it is completely blocked. That is the reason. Whereas if there is a optical path difference in the object and which affects this, and then these two rays will interfere and then emerge out as a elliptically polarized light in 3 dimension, and which will be partially transmitted through this analyzer as a resultant waveform, and that is how it will form an image. We will see the actual example in the optical microscopy lab. I will now go to the we will continue from this video, optical microscopy. Now we will demonstrate the DIC. What is the object which you are now seeing is a DIC setup. You can see that you have this DIC prism or Nomarsky prism or modified Wollaston prism, which can be inserted into this optical axis, and then you can see that there is an adjustable screw. Now we will see that what kind of contrast you get out of this microscopy. So you see that this is a similar specimen, that is a titanium alloy. What you are now seeing is like differential interference contrast. You can see that all your boundaries and other regions appear like white, and then it gives you a shadow. You are getting kind of a 3D projection or a surface relief by this setup. and we can also see that the twinning in the grains, which will be much more clear when we go to higher magnification. And let's slowly increase the magnification. Yeah, now it's getting focused, so you can appreciate the kind of contrast you get at a little higher magnification. You see that all these twins and then defects appear as if they are the three-dimensional images. You can see that a dark and a bright line which makes all these constituents, microstructural constituent, as if they are a 3D. We will see how this contrast is produced, and we also appreciate the moment you change the analyzer's orientation, the color of the micrograph changes. That means it will block a particular wavelength, and then you will start seeing the particular color. So you can keep on changing the orientation of the analyzer depending upon the orientation, and it will block a particular wavelength of the light, and then you see a multiple colored image. That is also an advantage of this DIC system. Now I will go to the blackboard and then draw some schematic of ordinary and extraordinary wavefronts in the image plane. We are now going to talk about the interaction of this ordinary and extraordinary wave, which is coming out of this beam, which is coming out of the beam splitter and then through specimen. This is the distance between these two. Let us call this is sigma 1 and this is sigma 2. Nothing but ordinary and extraordinary ray, and delta bias, and this is delta object. This situation is at extinction. That means your polarizer and analyzer, they are at the mutually perpendicular direction. And we have also seen in the polarized light microscope as well as DIC microscope, if you turn the analyzer to the particular orientation, you can see only a dark background and there will not be any image contrast. That condition is extinction. So this is corresponding to, this is a phase of these two rays, and the delta for this, that is a phase shift for this, or retardation I would say, is 0 here. And you can see that a corresponding, this is a phase versus distance, this is an corresponding amplitude versus distance. You see that so you see that since these two rays are not retarded enough, that is delta is almost 0, so you see that there is no amplitude contrast here. This is almost equal to 0, so it should come like this. This corresponds to 0, the amplitude is 0, so there is no contrast. So with the biased retardation, what happens? This is delta for object. And then look at the corresponding amplitude versus distance. The region correspond to these two. You see that so with a biased retardation between two rays, that is ordinary ray and extraordinary ray, you see that delta is increased, that is retardation, is a measure of retardation delta. So you see the corresponding amplitude which is increased to the peak and then decreased. So that means what? You will see the objects under the microscope. At one side it will appear brighter, the other side it will appear darker. So the brighter side belongs to this peak, the darker side belongs to this position, that is trough. Okay. So this bright and dark contrast of the constituents on the micrograph will give you a three-dimensional appeal and with the gray background. So that is how you appreciate the image contrast in the DIC microscopy. So now we will look at, or we will move on to the last variants of the optical microscopy called fluorescence microscopy. Look at this image, which again taken from this website. The fluorescence microscopy has gained in popularity ever since Kuhn's 1941 developed methods to conjugate proteins to fluorochromes, and as improvements in the optics, thin film technology and optoelectronics increase the specificity and sensitivity of detection of emitted fluorescent light. We will see very briefly what is the principles of this microscopic technique. Mostly it is being used in, as mentioned, it is thin film technology, biological sample and transparent samples and so on. We will now go through the principles and applications very briefly. So let us review the physical basis of fluorescence. I hope you have some idea about fluorescence, or you might have heard in your earlier classes. This particular schematic is known as Jablonski diagram. So if the fluorescent molecule absorbs the photons, and these are all the energy states, and we will first see the remarks and then we will come back to this individual transformation. Molecules that are capable of fluorescing are called fluorescent molecules, fluorescent dyes, or fluorochromes. If a fluorochrome is conjugated to a large macromolecule through a chemical reaction or by simple adsorption, the tagged macromolecule is said to contain a fluorophore, the chemical moiety capable of producing fluorescence. Fluorochromes exhibit distinct excitation and emission spectra that depend on their atomic structure and electron resonance properties. So if you look at the schematic, you see this, these are all the energy states. Once the photons are absorbed, the electrons move to an excited states, and you have some characteristic excited singlet states and excited triplet state and so on. And you can see that a lot of phenomenon, absorption and fluorescence, internal conversion, and then internal intersystem crossing and phosphorescence and so on. So what is that the fluorescence microscopy to do with this? We will see that. So there is something called a Stokes shift. That means once the absorption of the photon takes place, the vibration energy is lost when the electrons relax from the excited state back to the ground state. As a result of energy loss, the emission spectrum of an excited fluorophore is usually shifted to a longer wavelength when compared to the absorption or excitation spectrum. Note that wavelength varies inversely to the radiation energy. So you see that the schematic spectrum, absorption spectral profile, you see that it's in yellow line, and this is an emission spectral profile for some kind of fluorophore. You see that the emission spectrum has got higher wavelength as compared to the absorption spectrum. So, the primary idea is to separate these two and then see what kind of information one can get from this radiation or fluorescent radiation. So, the effective separation and detection of excitation and emission wavelength is achieved in fluorescence microscopy through the proper selection of filters to block or pass specific wavelength bands in the ultraviolet, visible and near infrared spectral regions. So, you should recall that in an introduction class we have also seen some of these filters and their characteristics. In this particular technique, these filters are going to be used. We will see how. The basic function of a fluorescence microscope is to irradiate the specimen with a desired and specific band of wavelengths, and then to separate the much weaker emitted fluorescence from the excited light. In a properly configured microscope, only the emission light should reach the eye or detector, so that the resulting fluorescent structures are superimposed with high contrast against a very dark or a black background. The limits of detection are generally governed by the darkness of the background, and the excitation light is typically several 100,000 to a million times brighter than the emitted fluorescence. In a fluorescence vertical illuminator, light of a specific wavelength or a defined band of wavelengths, often in the ultraviolet, blue or green regions of the visible spectrum, is produced by passing multispectral light from an arc discharge lamp or other source through a wavelength selective excitation filter. Wavelengths passed by the excitation filter reflect from the surface of the dichromatic, also termed as dichroic mirror or beam splitter, through the microscope objective to the specimen with the intense light. If the specimen fluoresces, the emission light gathered by the objective passes back through the dichromatic mirror, and it is subsequently filtered by a barrier or emission filter which blocks the unwanted excited wavelengths or excitation wavelengths. It is important to note that fluorescence is the only mode in optical microscopy where the specimen subsequent to excitation produces its own light. The emitted light re-radiates spherically in all directions regardless of the excitation light source direction. And this is the schematic which shows the arrangement of filters in the fluorescence filter cube. You can see that this is a light source which goes through an excited filter, and then you have the dichroic mirror, and then you have emission filter, and then a filter cube. This is a very simple setup, and then we will see how this works. If you look at the function of dichroic mirror, a dichroic mirror or a beam splitter is a special long pass filter coated with multiple layers of dielectric materials, specially designed for reflection and transmission at certain boundary wavelengths. So, it is a kind of a long pass filter, and let us look at what kind of action it does. And this is the transmission profiles of filters in a fluorescein filter set. So, this is schematic spectrum. You see that you have an excitation spectrum and an emission spectrum, and in a fluorescent microscopy, as we have seen, we have to separate these two as much as possible, and we will now see three different kind of high performance filter, how they perform the filtering. Look at this schematic plot where percentage transmission versus wavelength is plotted for the three high performance filter. So, one is barrier filter, another is exciter filter, and what you are seeing here with this blue line, which also includes this white region, is a kind of dichromic or diachronic mirror, which has very sharp filtering capability. We will see that the remarks first, and then we will get back to the spectrum again. The pronounced trough in the transmission profile, representing a peak of reflectance, is used to reflect the band of excitation wavelengths from the exciter filter onto the specimen. So, this is very sharp. You have the, you see that 100%, 0% transmission means 100% reflection of exciter filter, which will be falling onto the specimen. The boundaries between transmitted and reflected bands of wavelengths are designed to be as steep as possible to assure complete separation of the reflected and transmitted wavelength. You can see that you have a steep wavelength, a steep transmission difference here. It goes almost 90%, which separates the excitation radiation versus the transmitted radiation. So, which is very high performance filter. This is how it acts. It transmits or it reflects 100% the excitation spectrum, and then that means it blocks here. Transmission is 0, but it almost transmits 95% of the transmitted wavelength. In our case, it is a fluorescent radiation. And these are the typical micrograph obtained through fluorescent microscopy. What I have shown in the earlier classes in using a transmission optical microscope, these images were taken, and this is an image of a pollen. Biological people would have done some experiment with this. Pollen is a kind of a powder which comes from trees, grass, most of the plants, and this is one of the banyan tree root cross section, which we have seen in the phase contrast microscope as well as bright field illumination. It is a similar root which appears under the fluorescence microscopy like this. So, I think with this we will stop the discussion on all the optical variants. We will now move on to a next topic, that is how to prepare the samples for optical microscopy. So, in next class I will take up different steps one has to go through to obtain a good specimen in order to get a very good micrograph. And also we will see in a laboratory demonstration how each of the sample preparation steps are being followed to prepare a opaque specimen. Thank you.